Before we do this part of the lesson, let's do a simple antiderivative just so we get our terminology down. So the integral of x squared dx is x cubed over 3 plus c. This function right here represents a family of antiderivatives. This part of the function represents a particular antiderivative. It would be the particular antiderivative if c were simply 0. This integral to the left is considered an indefinite integral, meaning there are no bounds, and the result of that operation is to, in fact, return a general antiderivative. Now back to the family of antiderivatives. Let's call this the function g of x. Now the derivative of g of x would simply be the integrand, the x squared here. And that would be true for any c, because the derivative of a constant is always 0. A takeaway from this is that the integrand, no matter what the integrand is, it will always be the derivative of the antiderivative. That should be pretty obvious. Let's continue the lesson. Let's look at this equation right here, which has two players. One of the players is f of x, and the other player is g of x. It is clear to see here that based on the equation that's with a box, g of x is an antiderivative of f of x. And it is as equally as clear to see that f of x is the derivative of g. Now we can also summarize this relationship by saying g prime of x is equal to f of x. So, for example, if we were to say that g of x is equal to the integral of x squared dx, then it would be clear to see that g prime of x, the derivative of g, would simply be x squared. You may recall when we said that the derivative of an integral is simply the integrand. Well, that's what's going on here. Similarly, if we say that g of x is equal to the integral of the sine of e to the x dx, well, then obviously g prime of x would be the derivative of the integral, returning the integrand. Now, before we go and make this complicated, please let this concept just drive in your head, the simple idea that the derivative of an integral is the integrand. We're going to do some fancy stuff, but never get distracted from this basic picture. Now let's make this a little fancy. Now we're going to say g of x is equal to not an indefinite integral, but a definite integral, and this integral will have bounds. And the lower bound will be a. Now a can be any constant, and the upper bound is going to be the variable x. And because I put a variable in the bound, I have to put a dummy variable, f of t dt. This is a fancy way of saying what we already said up here. The only difference is we added bounds to this just to make it a little bit tricky. This is also so that we can discuss the fundamental theorem of calculus, part 1. And before we get distracted, we will say g is an antiderivative of f, and f is the derivative of g. Now, I'm going to write this a little bit more carefully. G of x is a particular antiderivative of f of x. Particular meaning we have an initial condition. In this case, g of a is equal to 0. Real quickly here, if you were to plug a for x, the integral would go from a to a, and that would result in 0. So g of a is equal to 0. Again, don't get distracted just yet. We'll say that f of x is the derivative of g of x, and we have this statement. That is the relationship Believe it or not, that is the fundamental theorem of calculus part 1. The fundamental says that if you have this equation, then we can define the two players in the relationship. We can define G to be the antiderivative, F to be the derivative, and that's it. That's what the fundamental theorem of calculus part 1 says. It's a simple translation of some notation to the particular relationship. And the consequence here is the same. If we take G prime of x, that's going to equal the integrand f of x. This is our big takeaway, but it shouldn't be that new or confusing. Let's take a look at an example. Here we'll say g of x is the integral from, now you can pick any constant you want, any constant whatsoever. I'm going to pick 1. That's the first thing that came to my mind. And it's going to be the integral from 1 to x. I'm going to pick a f of t. I'm just going to make this up and say t squared dt. Remember, t is just the dummy variable. The real variable is x. Okay, what I need you to do from this is to simply be able to find what g prime of x is. And g prime of x, the derivative of the integral, is x squared. That's all you need to be able to do. But wait, I know many students have a question. Wait a minute, how come this is 1? What if it were 100 or -7? How does that just go away? How does that disappear? And I don't quite understand how we have a dummy variable and then the dummy variable goes away. And that's what I want to do for you right now. I want to verify that this is true. Now, verification is not, I repeat, not something I'm asking you to do. I will do it in the notes so that you can put your mind around this and really cement the concept. So here, g of x is equal to the integral from 1 to x of t squared dt. Now I'm going to expand this, so to speak. I'm going to use what we know as the fundamental theorem of calculus part 2 to expand this. The antiderivative of t squared is t cubed over 3, and I'm going to take that from the lower bound of 1 to the upper bound of our real variable x. Employing the fundamental theorem of calculus part 2, that comes out to be x cubed over 3 minus 1 cubed over 3. Summary, g of x written in an expanded form is x cubed over 3 minus 1/3. Now I want to find g prime of x. Well, to find g prime of x, I first find the derivative of this first term, and that comes out to be x squared. And then the derivative of the second term, which is a constant, would be 0. So let's answer a question here. Suppose instead of this being 1, it was 100. That would make this 100, and then that would make this 100 to the power of 3. But even if that were so, even if that was 100 to the power of 3, the derivative of this constant term would still be 0. And in the end, I verify that g prime of x is simply x squared. Cha-ching, cha-ching. No matter what this value is. And the next example here, we will say g of x is equal to, heck, pick any number. I'll pick -2 to x. And then I'll pick something inside. Let's go with the sine of e to the t dt. The takeaway, the thing you need to be able to do here, very simple. G prime of x is equal to the sine of e to the x. The derivative of the integral is the integrand. We're not going to verify this one, and in fact, we can't verify this one. The indefinite integral is not what we say integrable. You can't integrate it. But we can still note that the derivative of the integral is the integrand. And these two examples here, if I ask you to find g prime of x, this should be almost brainless. It's simply the integrand But in terms of x, as we showed in the verification for this one, g prime of x, you guessed it, the square root of x. That is the fundamental theorem of calculus, and then this derivative portion is technically a corollary to the fundamental theorem of calculus, part 1.